Our next speaker is Taliver Heath, and he's a manager of power utilization and system health team in the platforms group at Google. So very good to have someone from outside come in and tell us why we're doing important work. And he's been at Google since 2005. Very good, very good. And one interesting corollary is that he spent 4 years teaching physics and reactor principles at the Naval Nuclear Power School. So I wonder what's in those healthy Google data centers. All right, great.
Interesting thing is, based off the previous two talks, I was realizing about somewhere between 12 and 18 orders of magnitude higher up the stack for power at this point. So the talk will be equally high level. So I apologize for not having a lot of electron microscope graphs, because those are really nice. Yes?
The title says maximizing data centers. Now, in our program, we wrote minimizing.
No, actually, in your program, you said maximizing data center power. I actually sent that title in as a tease to get people more interested in coming here to yell at me. But it really is efficiency what we're talking about, and we're about to jump right into exactly that. But it was fully a taunt to get people here to yell at me. So I'll go into that. All right, so we start with what is a data center? What's a big building where computers go in? And that's how everyone originally started. Is this a little button thing clicking? Is that what we're going to do? All right. So this is a little, everybody sticks their machines into a giant building and calls it a day. And honestly, that's what most people are thinking about in their head, but there's actually a little bit more that you actually have to get a data center to work. For example, you actually need to get data out of your data center. So you're serving this very important picture to people, so you need a network outside the data center. You also need to have a network inside your data center to put all these machines that you're putting there together. So you also need this other fabric in there. You might not realize this also. Turns out you need power to run these. I'm not sure if, it's not really on the top of a lot of people's minds, but you really do need electricity to get in there. So what that means is not only do you have to get this utility line comes in, you actually need to have an electrical substation in many places you put in there, so you get it from the transmission line down. You also need to have it actually putting the power and distribute that out to all the racks and to all the machines. You actually have to have all that big copper that's going in there. Then it turns out these machines make heat. And from my point of view, I tell people often that these things are a lot of basically network-connected space heaters from my point of view. And so you have heat coming out of it, so you need to actually get that heat away from these machines. So you have to cool that. Well, that means you actually have to have chillers and cooling towers to get that heat out of there. And those things, where am I going here? Click to go again? Yeah. And those things actually require water in a lot of cases to get those to work. And if you're bringing in water, a lot of times you actually need to have a water treatment plant as the water's coming back out the other side. So now you have this big data center, and we haven't even talked about the fact you also need backup power. So you're going to have generators on site, you're going to have batteries on site. And notice, suddenly, from my point of view, the actual whole point of these machines has started getting smaller and smaller. And all this other stuff is actually there that you've had to buy to make this data center work in the first place. So we actually have a fixed cost right off the bat to build a data center. You have the power distribution, cooling, machines, all of this stuff you have to buy. And so really, you're looking at somewhere between, about, say, $10 a watt to build a data center. So if you're building a 30 megawatt data center, that's at 30, that's now $300 megadollars, right? So that's like $1 Canadian these days, right? No, just, all right, so incremental costs, power usage, machine repairs, all of this also goes on to it. So the actual usage of your power adds on there. Electrical costs, basically, when you start looking at it, the non-electrical costs and everything else starts to become, your 5 cents per kilowatt hour you're talking about, 2 to 8 cents per month for everything else. These things start adding up and start making a significant amount for your system. So this 30 megawatt data center, you're now talking $300 to $750 million that you built this one building, and now the standard thing for clouds is to have 2, 3, 4, 5 of these buildings distributed around the world. So you have a lot of these. And your non-electrical cost, peak utility charge, all this stuff. So your capital expenditure is going to be between 56 and 67% of the amount of you're spending on this data center. Apart from the machines, you have to build all this infrastructure. Now, why am I telling you all this? Well, because this is what I do. Right? That's number one. Number two is because we don't build all this to put in machines that we don't power, right? You don't buy all this to not use that. So if you're going to get all, and that's going to be the main theme here, is once you've built all this data center, if you just put one machine in it, that's obviously a waste. Well, so how many machines can you put into it? The more machines I put into this data center, the more that cost is amortized over all of those machines. And the more that cost is amortized over all the machines, the more efficient, in a sense, from a capital expenditure this system gets. So, basically, yes. And before I put a single machine in is a very kind of like hand-wavy thing, because if you're clever, you're still building the data center while you're putting it in, right? So you have like your construction and stuff at all staged. So but hand-wavy, yes. Before you do any buying of machines, in the concept of money before you put in there, yes. So nobody ever got fired for over-provisioning power and cooling. Well, it actually starts mattering, right? So a 10% safety margin on infrastructure, you now just lost, $200 million that just cost you, right? 10% safety margin. So the more safety margin you get rid of, you're a little bit unsafe, but you're a lot cheaper, right? That's kind of the half and half game between. And really, what does safety really have to do with anything, right? Like, we're not going to kill anybody here. I mean, if that guy doesn't get his LOL catch picture, maybe not a huge issue. I got to start being careful here because I'm actually being recorded, so I'm going to have to start self-censoring a lot more as I say these things. All right, so improving utilization at the machine level. We had actually been talking about this. You guys actually been doing all of this at the hardware level. Very good job, and going into that. And let's look at a little bit where that goes to. So, of course, we could simply not use these machines, and that would make them use the least amount of power we could possibly do. Right? So, but the point is, we actually want to see how much work per watt we can get. And really, all this slide is going to is that static power kills you. Right? It's that static overhead that's going to eat you alive. So really, that's all this is talking about. This, just a little note to Benny, kind of off to the side, a little comment. I was warned about giving this talk about 2 weeks ago, so I couldn't go through and rejigger a talk to make it more official and more numery for people here. So because I already had to have one officially approved. So this one's in my back pocket. This one's actually given to college students. So if it seems very high level, it is. I apologize, but it lets everyone else participate a little bit more and talk and But we have, most of the official slides actually have sigmas and stuff on them and little pies and things. All right, so, okay, so work per watt. Option A, so what we can do then, if we want a higher work per watt, we can either build a cheaper building. That's actually, so let's talk about, we're going to try to figure out what we can do to, it's actually like kind of work per dollar is really what we're looking for here. So we can actually reduce the cost of all this overhead. We could build really cheap buildings. Then we don't care, right? That overhead, if buildings were free, I wouldn't be worried about this at all. We'd shove whatever machines you guys give us and we'd be good to go. On the other side of that, if we can build fewer buildings and shove more machines into it, that makes the buildings cheaper. And so that's actually in our control, and that's what we're working on now. So, we do 5% in a 30 megawatt data center. Basically, we're just talking about, we just made a $15 million investment. And we'll talk about software tricks we're working on to make that happen. Okay, so ways we can do this. This is all in the media and all over all the papers. You can do all these standard things. Lower processor, static power, that's what everyone's talking about. That's great, but actually does not solve my problem entirely for a different reason we'll get to in a minute. Dynamic voltage and frequency scaling. That turns out not to be great. We'll talk about that in just a second. Shutting down idle machines. The standard way in all computer science, or the operating system computer science research, turn off all machines has been the standard for about a decade now. Let's turn things off we're not using. And improving machine utilization. This is really what we'd love to do, but this is kind of hard. If we can make all machines always run at 100%, again, the job would be easy, right? Because that's, everything's using it as much as they can, then we just have a static hit, no problems. Instead, though, we have this problem where machine utilization is kind of tricky to get to go really up high. So we've seen that software development costs is actually kind of hard as you get to more and more parallel components, especially if you're using massive parallel operations, it actually starts hurting a lot more. So if you're just saying, we often see in papers, don't worry, someone will say in a DVFS paper, they'll say, oh, don't worry, your performance only has like a 0.01% hit. It's okay. It only slows down 0.01% of requests. You'll never notice. Yeah, if I'm serving your website, maybe, but if I'm serving out of 1,000 machines, that means 10% of all requests are now slower. That's money. That's like cash. And like cash is good, right? So we want higher cash, so we would not do that. All right, shutting down idle machines, again, makes a lot of sense unless you've done something like Google has of putting all your disks on all the machines so you can have a distributed file system. And if you have a distributed file system with your disks everywhere, you can't just shut them down all over the place because writing gets a little hard. We've actually, oh, you could shut down all the ones and just, you could read still fine from your replicas. Yes, so how do we write? We'll work on that later. Right, okay, that's usually a trick. All right, so now the really big thing is we can talk about is exploiting predictable workloads. And the fact is that we really, even when we build out these data centers, if you put in a machine, it never runs at 100%. It just, and especially if you look across all of them, every machine does not simultaneously spike to 100% in a data center. It just doesn't happen. Right? You just don't get that kind of, so you can start exploiting the statistical game of not every machine is going to go up to 100%. And we can even get crazier. We can actually look at things like, okay, we can actually look across all of our applications running and look at what their utilizations are and start asking the question, well, how many more could we put in there? And we find out that we can actually put in 40% more machines. So in other words, instead of assuming that each machine takes 100% of the rated power, the power the motherboard goes maximum, just assume they would run at 60% instead and deploy your machines like that. And if you do that and put in that 40% more machines, now you just saved about $200 million on that data center. Right? So that's by over-deploying it. Now, we start having a little bit of problems. This is, I like to call it the inverted Lake Wobegon problem. Like, not every machine can be below average at all times. So we start having this issue of how do you measure power consumption quickly enough to prevent breaker trips? You know, so because if the breaker goes off, yes, you're using a lot less power. Not the best way to use a lot less power. And, you know, what do you need to do to limit power consumption when you're nearing these breaker limits? So how do you handle this? And this is one of the reasons we don't use the DVFS trick too much. Honestly, that gets hard because turns out some applications are actually more important than other applications. Like the ones making money are less important than the ones not making money. And so you don't want to be completely fair to these two jobs. So you don't want to have a risk of you just slow down the processor, and you actually have to make sure that you're scheduling your jobs on the processors where they're going faster if they're making money. So this actually starts mattering as well. So you actually have to be clever when you're doing this. You can't just be blanket, oh, slow everybody down. No. Right? So how do you coordinate machine power consumption? Like, so actually now how do you move power from one side to the other? Something the research community sadly neglects pretty severely is this whole concept of reliability across many tasks and how do you actually keep everything up and across a system architecture and what are all the best practices? Because honestly, this gets tedious for researchers. Oh, it's a solved problem. You just do it right. How hard is that? Right? So, and it turns out that, you know, handling all these subsidiary systems is actually, you know, all these secondary supporting systems becomes a little bit tricky. How do you turn it off? So if you're running with this system and something's going wrong, how do you disable it so that most of your machines can keep running? And that's tricky as well. And so one of the things we've done is we have a system that we have the ability to turn off individual machines, and we've weaponized it so that it has to go out there and hunt individual machines and just turn them off very fast. So, you know, one of our nice little fun things. I call it weaponized. That's my Navy background because I just like calling it that. All right. And the majority of this, though, is software, not hardware stuff, right? This is majority of this was a software problem. This was a software talk too, so that's why, you know, we could talk a little bit about hardware. But the software problem in this case is how we're having to solve this because it's a distributed system that we're solving. The fact that, you know, you're looking at dynamic ranges, if you get rid of the static, you still haven't solved the problem because we still have dynamic ranges we have to care about. And what the fact is, we still put 60%. We still put the machines in as if they were using 60%. We just put in more. If you make machines use less power, the answer is that's awesome. We can put in more. That means we don't have to build another building. Right? And so honestly, that's how this is green. We're not going to build this other giant secondary system to support everything. Right? And that's really where the green of this energy efficiency comes in, is that really we don't have to build another system as much as, you know, using it. You know, don't think of it so much as using more power. Think of it as not building something else that uses more power. All right? And let's see. This is a fast talk. That's because I'm a fast speaker. Okay, I can go back. I can do it again. We can just go back and just do it twice. I got time. So again, the big thing here is that this data centers are more than a bunch of machines, and we actually want to use all this stuff we bought. Right? And so that's really the big lesson here. Whatever you buy, you want to use 100% to make it cheaper. Because if you don't use all the stuff you bought, you shouldn't have bought it. Right? And if you can say, well, if you're not going to use 60% of it, just build it 60% smaller. Exactly. That's the other way to do it, right? You could put in 40% more machines or build it 60% smaller. Either way, right? So better quality, work per watt is good. Efficiency, I thought I wasn't going to have time for this. I forgot the fact I talk really fast. And so I actually cut out like 6 slides out of this talk. One of the things I didn't go into in great detail was actually cooling efficiency in the data center. We actually have a lot of ways that we go about exploiting this and trying to bring the number as close to basically efficient as possible. Right now, for example, our data centers run somewhere between 1.12 and 1.2 power utilization efficiency, which means for every watt that gets to the server, 1.12 watts comes in from the street, and that accounts for all energy conversions and all the cooling. So it's a 12% overhead, and that's our officially released numbers that we make as high as possible so that no one can yell at us. But we have other numbers internally that usually point to they're even possibly a little bit better than that, but not official. Not official. All right. All right. So anyway, that's another way you can actually maximize this, is making sure that you can reduce your cooling overhead by not buying a bunch of cooling stuff so that you're very efficient in that sense as well. Okay, so all of this, every number I gave in here was from a publicly available source. All of them are cited, so feel free to go through, and all this stuff, the majority of it comes from Data Center Knowledge, so you can just go onto that site. It has the majority of our reviews on our stuff, as well as Urs Holt's book. So is there any questions? Because we have plenty of time.
Questions?
Yeah.
So you said, let's see, 1.12 watts from the street to put 1 watt into the processor.
No, sorry, into the server. So it's into the power plug of the server.
Into the server.
That's what the industry standard is.
Even so, that's fantastic. That means you're only using 12% of your energy for air conditioning, and that represents a fabulous coefficient of performance to use the air conditioning talk.
Yeah.
Okay. So how do you manage to do that? Because most often you have to waste a watt on cooling to get a watt into your machine. So how did you do that?
I will tell you the standard ways that this has been approached externally. So, because I can't, of course I don't want to, look, here's all our IP. I can't quite do that. So, the primary way, if you look at, so, let me see if I can phrase this. I'm now constantly self-editing here as I go. So let me see if I can do this. Okay. The fact that we own the entire stack helps us a lot. The fact that we build our servers and the data center ourselves allows us to do significantly better juggling between these. So we can, for example, tell people, internally we'll say, okay, this is the inside air temperature you can expect for the system. And they'll say, yeah, that's fine, you can even go higher. And we'll make it higher. And so because we have the people designing the servers to an expected temperature, and because they have an expected layout and an expected way the machines are going to be, and they have an expected interfaces that they can actually say, no, if you can make it do this, it's even better, and we can go back and juggle this. That kind of freedom, degrees of freedom, allow us to really push the envelope. So as opposed to something like if we went into a co-location facility, a lot of times they don't have that kind of degrees of freedom. They simply have to say, we will provide you with 62 Fahrenheit air at this many cubic feet per minute, done. And you can't tell them, well, we don't need that. No, that's what you get. That's what our systems are running at because everybody said that that's okay. So that's one of the ways that we kind of get to play with this. Other things, but if you go look on to some of the more open things like the talks that Facebook and Microsoft both put out with airside economizers and basically moving in directly air from outside. Other tricks you can play to pull that off. So it's
what is an airside economizer?
Basically a big fan. It's basically a giant fan that sucks air in from the outside when it's cold enough and pumps it directly through the data center and then back out the other side, so that you just have filters. And you just kind of hope that your climate's usually good enough for everything. And there are pros and cons to that approach. And that if you do that, then your location of your data center kind of says how your cooling is going to work. And then you have to design around that. So, but that's also fully available.
So that says you should put your data centers
So it says you push your data center to Canada, unless, yeah, and that's why you actually see a lot of them in Oregon, where it's, because you tend to want to look for dry and cool, right? So you tend to want to look for that kind of area. So Canada is good. Oregon over there, and actually not wet Canada, but the over here. But then you have to play the game of, and I've actually done site selection at Google also, so then you have to play the game of, though, well, how much does power cost? And it turns out the farther north into the middle of nowhere you go, the higher the power cost gets. It also turns out the farther north in the middle of nowhere you get, the higher the fiber costs get, and the longer latency. So if you get a really cold data center, if you put one in the South Pole, cooling is easy. But you have this other problem where now you have a data center that's just warming the South Pole. It makes the penguins happy, but that's about it. So, other questions?
There must be so much heat generated. You have so much power going into your data center.
Yes.
Do you have any capturing the heat to make electricity kind of arrangement?
So do we have
Power
anything that would capture the heat coming out of this thing? So the problem is, from a thermodynamics perspective, we're basically a heat sink, right? So you basically have concentrated electricity coming in, and you're spreading it out to a football field. And so now you're saying, can I take that football field worth of heat and turn it back into the power that goes in? And honestly, the answer is no. I mean, it comes down to it's such low quality heat that comes out. It's just not a very effective way to do it. Because if you start putting more and more layers to try to capture this, now you have more inefficiencies you have to build up and everything like that. So sadly, it seems like something you should be able to do with this heat, but it tends to be cooking marshmallows is about the nearby for the text. That's about it. So. Not even cooking as much as making them slightly warm. Yes?
A lot of...
Oh, it's running over. I'm just going to make you sprint around today.
The storage requirements obviously are growing quite a bit, right? And archiving. So Google is moving more from tape storage to more readily accessible hard drive-based storage, right?
Well, it's actually the other way around, but yes.
I mean, is that...
No, we use tape drives as backup. I mean, as archival, but everything's on our hard drives.
Is there any change in that strategy based on power, or?
Is there any change in the strategy of Google's storage system based on power? So let me go through the filter of, am I about to give away company secrets first? There has not been a significant change in the company strategy based on power of disk drive consumption. Because the nice thing is, over time, disk drives have gotten better and beefier for storage, but their power consumption honestly has not gone up. Right? Their power consumption is pretty much, still ballpark, 8 to 12 watts area. Right? So, roughly 15 if you want to it. I know I'm talking from my point of view of megawatts. Your 3 watts is huge. I know, but it's not too much different. So not really. So the disk drives keep getting bigger and bigger, so that's usually more than sufficient to handle the storage requirements.
Just related to that, since I was thinking about this, the trends you see, so you look at trends in 2006, right? And
yes.
You have these issues, and you look at those trends today, stitching that together, what's the thing that really scares you about the future? Like, have things not progressed in one area, and you feel like you're going to have to cover Oregon with power stations, or what's the looking forward, everything's fine, everything's changing at the same rate, and so it's fine, or what do you think?
So again, for people, for my vice president who will watch this video to see later if I really do need to be disciplined for saying anything in public for this. So in my world, I'm telling you my background's computer science and more software-ish than hardware-ish. So from my point of view, the problem is one of students not able to do proper basically not being able to take advantage of many, many, many cores. Right? That gets harder. From a programming perspective, doing serial to parallel conversions gets harder and harder. Now, the nice thing is Google's majority of our problems are ridiculously parallelizable, right? That's very easy. Shard it up, good to go. But the more complex things and the more complex interactions, the harder and harder it gets to use that many cores. So, and also the other thing that concerns me is failure domains, in all honesty. If you have 256 cores on one chip, and I have jobs running from who knows how many dozens or hundreds of people on that one chip. Now I have a failure domain of one chip that's going to take out 200 user jobs, right? Which is not the case now. So, and if we talk about, if you imagine a rack of those chips and how many processors would be in that for how many cores, now the loss of one cable to one power infrastructure has cost me how many thousands of tasks simultaneously. So that's a concern from my point of view for failure domain isolation. So that, and again, we don't want to stop you guys, but at the same time, that it's like job security for software engineers is really what that is. So yes.
So I know you cannot divulge the secrets, but do you have any rough breakdown, normalized, whatever, between the energy once you're in the server? Where does the power go in terms of the processor, memory, disk?
So, do I? Yes, but but I can't give it to you because we design our own systems. So I said, you just. I'm sorry. I can't go there right now. So I'm sorry. If you can find me at a bar later, we'll talk. But no, we won't. I'm going back. Yes. Sir.
Yeah. So you commented on the safety margin and down to the bottom line, a 5%, 10% safety margin costs millions of dollars if you're not utilizing that. How do you deal with something like that when you have to change out the processors or change out the servers every couple of years?
Yeah, it's kind of hard. No, so how do I deal with it when, like, if I'm going to be changing out servers and processors? Yeah, then you have to basically, again, because we own the entire data center, we're able to plan holistically. So we are able to say, remove this entire row of machines and put in this entire row of machines. So you can constantly replan for this well in advance. So it's not a onesie, twosie, replace this machine with this machine. It's done wholesale all at once. And when you get to play with that level of granularity when you have that number of data centers and size of data centers. So yes.
What can you tell us about the trends? What can you tell us about the trends for total power usage? Let's start with Google. So how fast is the amount of power going into the entire Google infrastructure? Is that flat? Is it growing? Is it shrinking? What can you tell us about that?
So I can tell you the stuff that we've announced, basically. And so if you imagine the fact that 2005 we opened Oregon, and so then we had, and think every building I say, imagine that's 30 megawatts, roughly. Just pretend, for sake of argument. So every building I say, that's why we pick 30. So every building we say is like roughly 30 megawatts. So 2005 we opened Oregon. 2006 or so was in Atlanta. 2007 it's North and South Carolina. 2008 it's Oklahoma, or it's Iowa, followed by Oklahoma now in 2009, 2010 timeframe. Belgium in 2010. And you have Finland that just opened this year, 2011. So you're talking somewhere between, like, just ballparking the number, somewhere between 30 to, like, averaging 30 to 45-ish megawatts per year increase in power utilization or power usage for just the data. And that's just by using it as data center bricks where we're trying to use them all up. So each of those bricks is using less of it, but if I'm just trying to give you rough ballparks, that's kind of what we're looking at there. Is that close enough? I mean, I can't give you.
Right now you're growing pretty linear.
Let's say yes. Well, honestly, right, so the trick is because it's linearly in power, which is not inappropriate. But like if you ask then, well, how many cores are you growing up by? That number then becomes different, right? So how much work are you getting done per watt? The work per watt is also going up. So growing power-wise linearly, yeah, you could pretend that. Would not be an inappropriate assumption.
All right, one last question.
Oh, sorry.
It's maybe financial. So we have like each year several hundreds of millions to spend for a data center. Where do you get all the money? I mean, it's like.
I'd like you to click on the ad for this talk afterwards, and it'll lead you right there. Yeah. All right.
All right, thank you very much.
Thank you. All right.